Let us see now how can we find the closed form for homogeneous linear recursions. These are going to be recurrent relations that we can express in this form. That is, all the terms are linear and equal to 0. And we are going to say that the recursion is of order R if the Sn term is expressed in function of k previous terms. In that case, we are going to need k initial conditions. For example, see the relation by recurrence that says that Sn is equal to 3 times Sn minus 1, with initial condition is 0 equal to. So let's observe this relation, Sn equals 3 Sn minus 1. So the n term is given in function the term n minus 1. So it's in function of one term. So the order of this relation is going to be 1. I mean, we can write this as Sn minus 3 Sn minus 1 equals 0. I mean, putting everything here in the same side, right? Putting this one subtracting. So we have the equation then written in a homogeneous linear form. And the order of this recurrence is 1. And that's why we have only one initial condition. Let's see this other example. In this case, the recurrence is given by Fn minus Fn minus 1 minus Fn minus 2 equals 0. So in this case, we see that it's already equal to 0. I mean, it's already everything in one side. And this is written in a linear way. So this expression is an homogeneous linear recurrent relation. And the order of this expression is 2, since Fn is given in terms of the two previous one. You also can check that the number of initial conditions is 2. So the order of this relation is going to be 2. Finally, this third example, we have given the homogeneous linear recurrence relation here. And again, this is an Sn that depends on the one before and the one before. I mean, two terms before. So that's why the order of this relation is 2. And we can see that that coincides with the fact that we have given 2 initial conditions. Now, given a homogeneous linear recurrence relation of order k, as we have seen a moment ago, with k initial conditions, we are going to define the characteristic equation of degree k, where k is the order of the recurrence relation. This equation is going to be a polynomial of degree k, I mean of degree whatever the order of the relation is. It's a polynomial then of degree k that starts with leading coefficient equals 1, and after that we go in decreasing order of degrees, k, k minus 1, k minus 2 until degree 0, and the coefficients are the coefficients of the recurrence. In other words, each of the Sn's that we have in the recurrence, we are going to change by a power of k. So the first one, that is always Sn, is going to be, in the equation, is going to be replaced by the power x to the k, where k is the order of the relation. After that, the next term is going to be, the coefficient is going to be the same one that we have in the relation. And Sn minus 1 is going to be substituted by a power of x to the k minus 1. And so on. So you are going to put the same coefficients in all and powers of x until the last term, that is going to be the one of degree 0, x to the 0, that is the one that corresponds to the last term of the relation. For example, let's see that we have the first of the relations that we were working with. So this one is already written here as an homogeneous relation. I mean, everything is in one side. And so let's take this relation and let's try to write the characteristic equation. So first of all, this was order 1, right? That means that Sn is in function of only the previous one, order 1. Or also you can say it has one initial condition. So because it's order 1, our characteristic equation, our polynomial, is going to be degree 1. And so we're going to start writing, instead of this one, we're going to put x to something. And this something is going to be the degree of the polynomial which coincides with the order. So in this case, it's going to be x to the power 1 because this relation was of order 1. And now minus 3, right? You see that we write exactly the same that we have in the equation, minus 3 times, and here we put a power of x, but 1 degree less. If the one before was 1, this is going to be 0, equals 0. So in other words, since x to the 0 is 1, right? So here this equation can be read as simple x minus 3 equals 0. Okay, and this is then the equation, the characteristic equation associated to this relation. Let's see the other examples that we were working with. Remember, this relation here is the order 2, right? So Fn relates to the 2 previous. And so because it's order 2, so we're going to start by writing the corresponding to this one, the term corresponding to this term, is going to be x squared. And a square because this relation was of order 2. And then we keep going, then copying the same coefficients. Here the coefficient is minus 1, x to the 1 minus 1, x to the 0, so just 1 equals 0. And that is then the equation, the characteristic equation associated to this relation. This other example, again, we can see that in here Sn is related to the 2 previous terms, so we can say that this one is order 2, and that is going to give us the degree of the characteristic polynomial. And so instead of Sn, I'm going to substitute by x squared because it's order 2. And then I keep writing the other ones in decreasing powers. So the one corresponding to this one is going to be x, and the one corresponding to this is going to be just a number. And the coefficients are going to be the same coefficients that we have here. So this is going to be minus 7x plus 12 equals 0. And then this is the characteristic equation associated to this recurrence. Now let us see what is the whole algorithm to find a closed form given the homogeneous linear recurrent relation of order k with k initial conditions. So the idea is, given the relation with the initial conditions, have to find a closed form. Remember, the closed form is Sn equals, and so here we should write an explicit definition of Sn, not in terms of previous terms, as is at recurrence relation, but in a direct way. The algorithm to do this will be, once that we have the equation written in a homogeneous way, I mean everything equals to 0, find the characteristic equation. And we know how to do that, right? So for the Sn, we're going to put x to the k, and so all the other decreasing terms until the degree 0, and the coefficients are going to be all the same coefficients that we have here. So the first step of the algorithm then is find the characteristic equation as we have seen before. Once that you have the characteristic equation, I mean, you take this equation and find the zeros. So here you need to be able to find the zeros of a polynomial of degree k. Find the zeros, and then let's suppose that the zeros that we obtain are these numbers, R1, R2, R3, until Rk, the k roots of this polynomial. And then, once that you have these k numbers, these are going to be numbers, right, the roots of the polynomial. Then, once that you have these k numbers, you are going to display them in this way. What does it mean this way? Well, you are going to set Sn equals to an unknown, let's call it A1. So an unknown times R1. R1 is one of these roots that you calculate here, to the n. So take the second of the roots and you are going to write again an unknown A2 times that number to the n, and so on with all the roots that you have here until you get the last one. And for the last one, you are going to write ak, that number, to the n. And so at this point, you will have a formula, let's say for Sn, you are almost there, only that these numbers, a1, a2, ak, are unknowns. So in the next step, you have to find those numbers. So find those numbers, and in order to find these numbers, you are going to use the only piece of data that you haven't used yet, the initial conditions. So by using the initial conditions, you are going to form a system of equations whose solution is going to give you these unknowns, variables that you introduced in the previous steps. Once that you have these numbers, then you come back to your formula for Sn, you put the concrete numbers there, and that will be your closed form Sn corresponding to the recurrence form of order k. Let's see an example how to perform each of these steps in a concrete relation. So let's see, for instance, if we want to calculate the closed form for this relation. The relation is written in homogeneous form, so we are ready to calculate the characteristic equation. Observe that this relation is of order 2, right? Either by looking that Sn is given in terms of the two previous, or just checking the number of initial conditions is 2. So we know that the order of this relation is 2, which means that the characteristic equation is going to be a polynomial of degree 2. So the first step is going to be find the characteristic equation. In this case, as we know that this relation is degree 2, we are going to substitute this one by x2, right? So x squared, because this is degree, is a relation of order 2. And then we keep copying the rest of the equation here, minus 7, and this one will be substituted by 1 degree less, right? So this is x squared, that will be x, and so plus 12, and this will be substituted by 1 degree less, that is just x to the 0, which is just 1, equals 0. And so this is then our characteristic equation. So that's the first step of the algorithm, find the characteristic equation. The next step will be find the zeros of this equation. In this case, this is just a polynomial of degree 2. We can calculate by quadratic formula right away the two roots of this polynomial. So then this is going to be 7 plus minus the root of 1, which is 1 over 2. So here we can see that the two roots are going to be 7 minus 1, which is 6 over 2, which is 3, and 7 plus 1, which is 8 over 2, 4. So then the two roots of this polynomial are 3 and 4, and that finishes the second step of the algorithm, that is finding the roots of this polynomial. The roots or zeros of that polynomial are going to be 3 and 4. And then in the next step, we have to arrange these two numbers, 3 and 4, in this way. Remember that the way to set Sn here will be to say Sn is equal A, an unknown, times the first of the root, or any of the roots, to the n, plus another unknown, and then the second of the roots to the n. So that is what equals Sn. Something, a root to the n, plus something, the other root to the n. And the order does not matter. And then we are almost there. We almost have the closed form, right? So we almost have what is equal to Sn. Only that these A and B are unknowns. So the next step is to actually find out what numbers are those. Solve for the unknowns. And the way to solve for the unknowns will be to set a system of equations using the initial conditions. The idea is, you have here a formula to calculate Sn for any n. So in particular, you can use this formula to calculate S0. So you can plug in 0 in this formula and you will get that S0 is A times 3 to the 0 plus B plus 4 to the 0, right? So this is just substituting here n by 0 and substituting that in the whole formula. So we can find S0 using this formula, but S0 is also given as a data. So what can we do? The thing that we calculate by the formula, we can say, well, that actually have to be equal to 4 because we were told that S0 is 4. And this is an equation. This is an equation that depends on A and B. So simplifying here, 3 to the 0 is 1, so this will be just A plus 4 to the 0 is 1, so we just A plus B. And so that's where this first equation comes from. S0 equals A plus B equals 4. We do the same with the initial condition S1. So we can calculate S1 here by plugging in here a 1. So that will be S1 equals A times 3 to the power 1 plus B times 4 to the power 1. So that means 3 to the 1 is 3, so this is 3a plus 4b. So we calculate S1 just using the formula. But we know that S1, we also have given the value as a data. So we know that S1 is equal to 4. So we can say, so then this is equal to this. And that is the second equation that will give us the values of A and B. So now, once that you use the two initial conditions to get these equations, you have here a system of two equations with two unknowns. Solve this system now by any method you know. I mean, if you know an elimination, that's the most efficient way to solve a system of equations. I'm going to use elimination to solve this system. I'm going to multiply the first equation by minus 3. So that will be minus 3a minus 3b equals minus 12. And the other one, I'm going to leave it as it is. So that will be 3a plus 4b equals 4. I just add this equation. 3a minus 3a cancel. 4b minus b is b equals minus 12 plus 4 is minus 8. So then I have the first of the unknowns. And having one of the unknowns, you substitute in any of the equations and you have the other one. So for instance, I substitute in the first one, a plus b equals 4. I substitute the value of b, and so a minus 8 equals 4, which says that a is equal 4 plus 8, a equals 12. And that's the second value of the unknowns. And then once that we have the two unknowns, so now this equation that we have here in function of a and b, now we know that a is 12 and b is minus 8. Let's just substitute these values there and we will have the final closed form. Then this is the final result by substituting here, right? So I'm putting a equals 12 and b equals minus 8. So this is then the closed form associated to this recursion relation with these initial conditions. So let's see this quickly, the steps in this other one. So you have in this case given this other relation with these initial conditions. Observe that in this case this relation is also of order 2 as before, and so the characteristic equation will be a polynomial of degree 2. Observe that in this case it's not everything equal to 0, so the first step will be to put it as a homogeneous equation. That will be to say that this is Sn minus Sn minus 1 minus 2Sn minus 2 equals 0. So from this equation in homogeneous terms, so we can see that the characteristic equation, the first step, will be to say, well, this one will be then x squared, and so here will be minus x, and here will be just minus 2 equals 0. So we have the first step, which is calculating the characteristic equation. This is our characteristic equation. So now we're going to go to the next step, which is calculate the zeros. Again, you can apply quadratic formula here, and you will get that the two zeros are 2 and minus 1. With the zeros 2 and minus 1, you set up the formula as we said before. Sn will be equal to certain unknown times 2 to the n plus certain unknown times minus 1 to the n. This is the generic form of Sn then in function of these unknowns a and b. So in the next step we need to calculate how much is a and b by using the initial conditions. We calculate S0 using this formula, and you make it equal to 2. That will be your first equation. Then you use the same formula but for n equal 1, and you calculate S1. When you have the formula of your S1, you make it equal to 7. And then you have here the system of equations given by the initial conditions. Now you solve the system, and you will get that the numbers that solve these two equations are actually 3 and minus 1. With these two values, we go to the general form and we calculate the particular form with these initial conditions, which is just this generic form, but putting in value of, in place of a and b, the two concrete numbers that you found here. So then the final form, closed form for this relation will be this one. So in this way, you can find the terms of this sequence. Here, by just substituting values of n, you can calculate the terms of this sequence. And here, by calculating each term in function of the two previous, we should be able to calculate the same terms of the sequence. Since it's the same sequence, right? In the first case, given by recurrence, and in the second way, given in a direct form. And if you feel inspired, you can come back to the Fibonacci recurrence relation and find the closed form. So the steps are exactly the same. The only is a little bit more complicated because of the algebra, the numbers that appear there when you find the roots of the polynomial, but otherwise it's the same process, the same way to calculate the closed form. And you will see that this is the actual closed form. The final result for the Fibonacci will be this, which is very surprising that with these numbers all involved with this square root of 5 and all that. The idea is that when you start to substitute f0, f1, f2, f3, f4, these numbers are the Fibonacci numbers. I mean, this sequence of integer numbers that you are familiar with now. It is kind of surprising and even magic to see that these numbers that we obtain here just by adding the two previous ones, right? And these very integer numbers, 0, 1, 1, 2, 3, 5, 8, 13, etc., are obtained by this formula. I mean, when you plug a 1 here, for instance, you do all these operations, you should obtain 1. When you plug a 3, you do all these operations, and you should obtain just 2. Moreover, this formula involves this very famous number in mathematics, what is called the golden ratio. a very famous number which is approximately 1.6, and it was known already to the Greeks, who named it as golden ratio, since they believed that the rectangles that have this relation, this ratio between the sides, are the most pleasant rectangles to the eye, the most pleasant to look at. That's why the golden ratio appear in art and architecture, but also have many implications in mathematics and in general in sciences.